Welcome to clickmyproject.com.
Our title: KDE-Track and Efficient Dynamic Density Estimator for Data Streams. And this is abstract. Recent developments in sensor, global versioning system, devices and smartphones have increased the availability of spattered improved data streams. Developing models for mining such streams is challenged by huge amount of data that can't be stored in memory. The high arrival speed and the dynamic changes in data distributions density estimation is an important techniques in stream mining. For a wide variety of applications, the construction of kernel density estimators is well studied and documented. However, existing techniques are either expensive or inaccurate and unable to change the capture in the data distribution. In this paper, we present a method called KDE-Track to estimate the density of temporal data streams. KDE-Track can efficiently estimate the density functions with linear time complexity using interpolations on a kernel model, which is incrementally updated upon the arrival of new samples from the stream. We also propose an accurate and efficient method for selecting the bandwidth value for the kernel density estimator, which increases its accuracy significantly. Both theoretically analysis and experimentally validation shows that KDE-Track outperforms a set of baseline methods on an estimation accuracy and computing time of complex density structures in data streams. Recent advances in computer technology allows for collecting vast amount of data that arrives continuously in data streams. Examples of data streams can be found in fields such as sensor networks, mobile data collection platforms, and the network traffic. The data needed to be processed and analyzed once they arrive. However, the unbound and rapid continuous arrival of data streams disallow the usage of traditional data mining techniques. Therefore, the development of an algorithm for processing the data streams instantaneously became highly important. Density estimations have been widely used in various applications. Estimating the probability density functions for a given data set provides knowledge about the underlying distributions of data constantly. Dense regions can be recognized as in clusters, and quantities such as medians and centers of clusters can be computed. By contrast, sparse regions are reported as an outliers that can be used for fault detection. Example in sensor networks. In this paper aims to estimate the dynamic density that comes with an evolving pattern of data streams. More than 170 billion taxi trips were recorded in the city of New York. Monitoring and visualizing the density of spattered temporal streams with the help of raising taxi cabs, reducing ambulance emergencies. However, estimating the dynamic density that comes with evolving spattered temporal streams is a challenging task. Besides the problem of estimating the density using samples drawn from an unknown distribution in case of stationary data, spattered temporal data streams have more challenges properties that complicate the estimations of density. First, the data distribution changes dynamically in an unpredictable fashion. Therefore, density function estimation should rely more on recently received data samples. For example, by using a sliding window second and an anytime available model should be efficiently operated to allow real-time monitoring of density. Meanwhile, the density function values of any new arrival data may need to be instantly estimated. Third, the spatial non-informative data distributions requires higher resolutions in dense area and lower resolutions in sparse area, so that the estimation is accurate to catch the detail. And this is our project flow. In this we will be having a data set which is the first step of loading data set. Then we will be having a pre-processing data set process. In this pre-processing data set we will be getting a true data deduction. And after getting a true data deduction, we need to get a spatiotemporal data from that true data, so that we will be extracting a spatiotemporal data streams in this. After extracting in this, data stream mining will be carried out. In this mining process, we will be carrying the cluster formations and the microcluster formation. After forming the microcluster formation, density analysis will be taken for the microclusters. In this density analysis, we will be generating a shared density graph. By having the shared density graph, we will be again analyzing and estimating the accuracy and the compute time of complex density structure. By this, we can able to recluster the data stream mining, so that we can able to have a density estimation in this. This is our project. This is a home page with the title KDE-Track and Efficient Dynamic Density Emulator for data streams. By clicking over the data, we will be starting our project. First we need to load our data streams. I will be just loading. Data streams are get loaded. After loading, we need to view the data sets. In this, first we need to view data sets loaded successfully into our repositories. These are the data sets. Which we get loaded, and after this loading, we will be pre-processing the data. In this pre-processing the data, just click on the pre-process get success. After this, view the data which are true information directed. After directing this true information, just view the only the true data which have been get directed. Then click on next. In this, we will be forming a cluster formation. We will be forming a cluster formation. Just click on the cluster 1. These are the clusters 1 and cluster 2 and cluster 3. These are 3 clusters which will be get formed based on our data sets loaded. Microcluster formation. By using this cluster formation, we will be getting into a microcluster. Microcluster 1 nodes. These are the nodes which are get created based on the clusters. The microcluster 2 nodes get created. These are the nodes again will be get created. You can see here null values have been get stored in this. Our next step is to remove those null values. In this, you can able to see null informations which have been get inserted in the microclusters. So we need to remove all the inactive microclusters. Removing process will be taken. View the process. Microcluster 1 nodes. In this, you can able to see all the clusters only with the data, and the clusters and the nodes without the data will be get erased in it. You can able to see only 10 nodes in this. Only data which have been inserted will be get inserted in it. In this, only 8 node. Empty clusters have been deleted automatically. In this, we can able to calculate the density calculations. By using this microcluster, we will be calculating the density. First, for microcluster 1, density is calculated. This is our density for microcluster 1. On microcluster 2, this is our densities, and for 3, and this is our densities. A cluster density inside a cluster has been deducted. These are the density inside for cluster 1, cluster 2, and cluster 3. We will be creating a density graph based on these values. And these are the density graphs, and this you can able to see the lower density occurrence for 3 clusters right now. Then based on this density graph, we will be recluster the data stream which can get loaded. Load recluster streams. By loading this recluster stream, you can able to see the difference of first loaded data sets and now loaded streams. And recluster graph can able to view the densities between the 3 clusters after getting the reclustering. This is our result, and thank you.